All right, so this is the practice exam 3 review for posterity. We are currently in the spring semester of 2024. So if you are watching this video in any other semester, there might be some information that's just specific to semester. But yep, anyway, like I said, spring 24. And let's review for exam 3. So our first question. We've got the simple harmonic motion of some object is modeled by the equation given here. D is equal to -8 cosine of 6 pi t, where D is in inches and T is in seconds. Provide exact answers and use correct units. We want to make sure that we get that part right as well. So to kick things off, part A is going to ask us for the maximum displacement of the object. And don't forget that the maximum displacement, just a more different way of asking for the amplitude. So over here, I need to pay attention to that -8. The maximum displacement is just the absolute value of that number. So the absolute value of -8 is +8. And to include the correct units, this should be in inches. Since our distance is being measured in inches. Right, whenever our distance gets measured in, that's the units we should have for the maximum displacement. Generally, it'll be some kind of a distance, so inches, feet, meters, centimeters, something like that. This one, ask for it in inches. The time required for one oscillation, just a different way of asking for the period. And we remember our formula for period is 2 pi over b, where here b is 6 pi. So our period is 1/3. And to put the correct units on here, we'll pay attention to the fact that time is measured in seconds. And the period for a simple harmonic motion object is usually going to be some kind of time. Not too many units for time. Seconds, minutes, hours, something like that. Seconds for this one, though. Then we want the frequency. And I think the easiest way to get the frequency is to say it's just the reciprocal of the period. The period and frequency are always reciprocals of each other. So the reciprocal of 1/3 is 3. And the frequency will always be measured in units of per time, or oscillations per time, revolutions per time, something like that. So oscillations per second in this case. And specifically for oscillations per second, we could also call that 3 hertz. Since hertz is the specific, it's the specific unit for a per second thing. Something that happens per second can be measured in hertz. It's about the only frequency unit that gets its own name. All the others would just be like oscillations per minute if we were measuring in minutes, or oscillations per hour if we're measuring hours. But as long as we're measuring in seconds, we can use hertz for frequency. All right, and that's question number 1. All right, question number 2. We've got a toy rocket is going to be launched from the ground, aimed toward a big tree on the other side of a privacy fence. If it's 21 feet from the launching platform to the base of the fence is 9 feet tall. We'll try to find the minimum angle of elevation we need to clear this fence. So we've got this. We'll start by drawing in a ground. That should be step 1. Cool. So there's a ground hanging out there. We've got a tree over on the other side of this fence. That looks like a decent trunk. Cool. We've got a tree. We are aiming our rocket, which is 21 feet away, at this tree. So that might be the trajectory of our rocket, could be that line. And somewhere on here, we've got a 9-foot tall privacy fence. So we'll draw that in. Okay, so here's our diagram. We have a right angle here where the ground connects to that privacy fence. The other labels we could throw on here, we know that that fence is 9 feet tall. We put 9 feet as our label right there. The rocket platform is 21 feet away from the base of the fence. So 21 feet, can go right there. And the thing that we are looking for is the minimum angle of elevation. And it looks like we'll round to a whole degree. So the smallest whole degree angle of elevation that clears the fence. So if I'm going to set up some kind of an equation that'll let me solve for an angle, I know ultimately I'm going to need an inverse trig function in order to find theta. Because anytime I'm looking for an angle, I always need an inverse function to find it. Because that's how the inverse functions, that's how they work, right? The solution to an inverse function, an inverse trig function, is an angle. So I need an equation that's going to put my angle together with its opposite side and its adjacent side. Since those are the two legs I know. Well, my opposite side is 9. My adjacent side is 21. Which means we probably want tangent of theta. So tangent of our unknown angle theta is opposite over adjacent, or 9 over 21. Then to get theta by itself, take the inverse tangent of both sides. So theta is the inverse tangent or the arctangent of 9 over 21. And if you put that into a calculator while you are in degree mode, it should give you 23.2. So 23.2 degrees. And then we want the minimum whole number angle of elevation that clears that fence. So 24 degrees should be our answer. So notice I'm rounding this thing up even though my first decimal is 0.2. Generally, we'd round that down. But by the phrasing of the problem, it's asking for the minimum angle in whole degrees that clears the fence. And so if we rounded this thing to the nearest angle, which is 23 degrees, it's going to be just underneath the top of the fence. So the minimum angle in whole degrees is 24 degrees, even though 23.2 should have rounded down. Small little semantic thing. Don't expect us to be that nitpicky on the exam. But hi. The exam should specify the number of places we want you to round to. If the question doesn't say specifically, just ask your recitation instructor. But yeah, it should tell you within the text of the problem how many places we want. Yeah, it's like this one specifically said in whole degrees. So round to the whole degree number. In fact, I'll highlight that. Minimum in whole degrees. All right. Let's take a look at the next one down. All right, finding the exact value of the following trig expression. Clearly show and label any reference triangle used. Highlight that in here too. Because we'll need a reference triangle to solve this one. So I want to get the cotangent of the cosine inverse negative 63 over 65. So usually start by pointing out that the cosine inverse of this number, cosine inverse of negative 63 over 65, that thing is just an angle. Right? Whatever results I get there, it's an angle of some kind. The answer to any inverse trig function, if it exists, is always an angle. So I'm really looking to calculate the cotangent of some angle. And I know that cotangent is going to be adjacent over opposite. Adjacent over opposite. So I'm going to create a reference triangle based on the information I have for the angle that I've called alpha. And then once I have that reference triangle fully completed, I can then just find the adjacent, the opposite sides. So that's my game plan. So let's break that reference triangle down. I should come back and look at my cosine inverse function. I know I'm taking the cosine inverse of a negative number, which means that this reference triangle should be put in quadrant 2. Since cosine inverse, negative numbers all end up in the second quadrant. So I'll draw my reference triangle over there. Shapes, just get a coordinate axis going. Slide it maybe over here. Draw what's hopefully going to be a decent right triangle. Yeah, close enough. Reposition that to be in the right spot. Said be in the right spot. Yeah, close enough. All right, so that means the angle. The angle that cosine inverse would spit out is that red one right there. It'll be just more than 90 degrees. Taking the cosine inverse of negative 63 over 65. So 63 will be my adjacent side, 65 will be my hypotenuse. And because we're in the second quadrant, negative should be placed on the 63. So my missing side, I'll give a label, and I'll call that y. I can use the Pythagorean theorem to figure out what y is. So I'll start with y squared plus 63 squared. Right again, plus 63 squared is equal to 65 squared. And then I'll solve that thing for y. Question real quick. So question from chat. Could I also draw that reference triangle in quadrant 3, since cosine is also negative there? And no, I could not. I'd get an incorrect answer if I did that. Because this is specifically cosine inverse, my reference triangle must be placed in either quadrant 1 or quadrant 2. Because those are the only two quadrants where the cosine inverse function is defined. So even though cosine itself can be negative in quadrant 3, cosine inverse will never be in quadrant 3. So because we had cosine inverse defined within the text of the problem, we are stuck in quadrant 2. Can't go anywhere else. Oh, but to finish solving for y, this will be y squared is equal to 65 squared minus 63 squared. Throw that in a calculator, you should get 256. Meaning that y is plus or minus the square root of 256, and that's 16. Now, because we're in the second quadrant, we should take the positive y value, because y is positive in quadrant 2. So y is going to be positive 16. And finally, come back to answer the original question. I want the adjacent side over the opposite side. My adjacent side was negative 63. My opposite side, I just solved for 16. So in the end, negative 63 over 16. Negative 63 over 16. Over here. So a follow-up question from earlier. So if it was cosine inverse, but with positive numbers, it would be in quadrant 1 every time? Question mark. And yes, that's correct. if we're taking the cosine inverse of a positive number, it always comes out in quadrant 1. Hi there. Oh, yeah, for sure. So the steps I took before I did the reference triangle. Didn't need to do them at the beginning, but I figured I'd start with the more like broad approach to the problem. So I know I'm taking the cotangent of the cosine inverse of something. Right, and I'll ignore the something for just a second. Cotangent, cosine inverse. I know that the result of cosine inverse is an angle. So I'm really just taking the cotangent of some, of some angle. And I know that one of the definitions for cotangent is the adjacent side divided by the opposite side. The which minus sign?
Cotangent 63 minus 65.
Oh, this negative up here, or this right here?
Over one. Over. Yeah, right. This might be blind.
Oh, right, yeah, right here. This is just an equal sign. Yeah. Mhm. Yeah, right after the set of parentheses, it's an equal sign. Yeah. Yeah, otherwise we wouldn't really have a complete equation there. Okay. All right. All right, let's move on to the, never mind. Hi, take a question first.
Just to make sure, for first sine and then first tangent, would they also still be in quadrant 1 if the number were positive?
Yes, so question was, if we had inverse sine or inverse tangent, would they still be in quadrant 1 if it was positive? And yes, all 3 trig functions are positive in quadrant 1. Yeah, that's the, in fact, every time we can, we want to be in quadrant 1, just because it's easiest there. But I'm sure we're going to run into a question like that in the multiple choice section, which is next. So let's see what we've got here. Finding the exact value of the secant of the tangent inverse of square root 3. So if we just solve that thing out real quick, the tangent inverse of square root 3 is pi over 3. So I can start by just solving that a little bit. Start on the inside and work my way out. Tangent inverse of root 3 is pi over 3. So then I've got the secant of pi over 3, which is the reciprocal of cosine, pi over 3. That's going to be 1 over 1/2. And the reciprocal of 1/2 is 2. That over there. So secant of pi over 3, or secant of tangent inverse of root 3 is 2. Those are the steps I'd take to get there. I'm moving on to the next one. I want the arc sine of the tangent of 3 pi over 4. That'll be the same as the arc sine of -1. Since the tangent of 3 pi over 4 is -1. Try again. And then arc sine of -1 is negative pi over 2. So B is going to be our correct choice. Specifically, 3 pi over 2, though, won't be correct. Even though the sine of 3 pi over 2 is -1, the sine inverse of -1 is always negative pi over 2. And we can't get any other answer from a sine inverse function. Cool. Right. On to number 6, finding the exact value or values of tangent inverse of -√3/3 is /r. Let's start by just approaching the trig question that's in here. Tangent inverse is a function And an important property of functions is that there's only ever one output value for a given input. So there can only be a single solution to a function. If I'm plugging in if I have a specific value I'm plugging into a function, there can only be one output. Since if there were more than one output, we'd be breaking the definition of a function. So this question is meant to trick you slightly, because it's trying to prey on the idea that both 5 pi over 6 and 11 pi over 6 have tangent values of -√3/3. But neither one of those is the correct answer to tangent inverse -√3/3. Because that thing has to get defined over into the -4th quadrant, the only correct answer is -π/6. So don't fall victim to that trick, because it's not 5 pi over 6 or 11 pi over 6. Hey there. Gotcha. So for number 5, solving out tangent of 3 pi over 4. Why did it come out to -1? So we're at a pi over 4 class of angle, where all the tangent values are 1 or -1. It's both sine and cosine are √2/2. But we're in the second quadrant with 3 pi over 4, and tangent is negative in the second quadrant. That's where I got -1 from. All right, let's take that on to question number 7. Finding the exact value of the cosine inverse of the cosine of -π/3. This one's going to come out to π/3. But let's show the steps that got us there. Working from the inside out, I need the cosine of -π/3. Remember that cosine is an even function, so the negative on the inside doesn't change anything. So the cosine of -π/3 is the same as the cosine of π/3, both of which are 1/2 and +1/2, because we're in the 4th quadrant. Then cosine inverse of 1/2 is π/3. Those are the steps I'd take to get there. Hi. They do kind of cancel out, right? Under the best of circumstances, they'll just cancel each other out. But oftentimes we end up outside of the very limited scope where cosine inverse is allowed to operate. So like cosine inverse is not allowed to operate in -π/3, because it can only be in the 1st or the 2nd quadrant. And -π/3 puts us into the 4th quadrant. So you have to do a little bit of work in order to cancel out the cosine inverse and the cosine. So as you can see, we don't get exactly -π/3 when we're done, +π/3. But there is certainly an element of those two functions canceling each other out. Yeah, just have to be careful about your domain. Or your range, I guess. Right, if we take this on to number 8, working with similar triangles. Let's see what we've got. ABC and PQR are similar. We want to find the length of side B. So notice that the sides aren't labeled directly, but all of the angles are. So we should be able to infer which side is length B. Specifically, length B should always be opposite angle B. So it's got to be that side that connects A and C together. Meaning it is similar to that 8.1 over there. So I should set up a similar triangle equation, which should say that B over 8.1 is equal to 2.7 over 3. 2.7 7/3. Since I'll look at the other two similar sides that I have to compare, which are the 2.7 and the 3 right there. So it looks like triangle ABC is 90% of the size of PQR. Since 2.7/3 would get me to 0.9, 90%. Oh, but to solve that equation for B, we are going to get 2.7/3 multiplied by 8.1. And I think you could just throw all that into a calculator. But I got 7.29. Option C. Right, when you're setting up one of these similar triangle equations, make sure that you're consistent with the side that you put on the top of the fractions and also on the bottom of the fractions. Since I put B on the top of the first fraction, I also want to put triangle ABC on the top of the second fraction. The 2.7 is in the same triangle as B is, so it stays on top. 8.1 and 3 are both in PQR, so I put both of those on bottom. It does not matter specifically which triangle goes on top, as long as you're consistent between the two fractions. So I usually like to put the thing that I'm solving for on top, because it just makes my work a little bit easier. Right. And one last multiple choice question, this time back to simple harmonic motion. So we've got an object attached to a coil spring is from its rest moving down a distance of 9 millimeters. Assuming the motion is simple harmonic with a 1/6 of an oscillation per second. And then find the equation that puts all this together. So let's start by looking at some of the words. From its rest moving down. Those words make this thing look like a sine equation. It's starting at its rest value and then it's moving down rather than being pulled down and released, which sounds more like cosine. This thing starts motion from its rest position and then goes down. So looking at some kind of a negative sine equation. Looking through all of the options, they all have -9 for A. So we didn't need to worry about that part, but we do want to get rid of anything that says cosine. So none of those are going to work. It's gotta be a sine function. That 9 millimeters tells us that is our amplitude. So let's come back to the other piece of information that we have, which is that we have a 1/6 of an oscillation per second. Now, an oscillation per second sounds like a frequency. So this thing is telling us that our frequency is 1/6, which means that our period is 6 and B should be 2π/6 or π/3. So I want the equation that has a B value or an angular frequency of π/3. And that thing is this one, option E. That's the one that puts all three pieces together. -9 for A, a sine function, and π/3 for B. All right. Moving on. Another word problem. This one's got a bearing involved. So let's see what we've got going on. Runner begins at the starting line of some race, presumably proceeds in a direction of 72 degrees west of north, 3.5 kilometers till she reaches the refueling point, turns 90 degrees southward, running 6.5 kilometers to the finish line. Figure out the bearing from the start to the finish. So let's do that. Right, so this will be our starting point. Right here. Start. So we are going to head 72 degrees west of north. So to draw that bearing in, I should start at north. If I just read my bearing angle from left to right, start at north, then go 72 degrees to the west. West would be left of north. Looking at it that way, so it should turn this way. Might as well get an accurate drawing here. Our angle should be right here. All right. Runner goes for 3.5 kilometers in that direction. 3.5 kilometers. And then is going to make a 90-degree turn southward. So basically just get to that point. Southward is going to be left. So turn left by 90 degrees. And then we go another 6.5 kilometers in this direction. So 6.5 kilometers. All right, and ultimately we're going to look for the bearing from the start to the finish. So I'll draw that angle in. Or draw in the line that connects start to finish. All right, looking at that. So here's our finish line. So that's step one. It's just getting our diagram drawn in. Should look something like that. Start by going northwest, then we make a turn to the south, and ultimately have a right triangle. So to label the angles on here that we care about, our initial bearing angle was 72 degrees. It was to the northwest. The bearing that we are looking for goes from start to finish. So from south connected over to that line. Use beta for the bearing angle. So that's the thing that we're hoping to solve for. But the angle that we can actually get based on a triangle is that one right there. I'm going to call it theta. It's the one on the inside of the triangle that I drew. So if I'm ultimately looking for the green angle, I should notice that all three of these angles in color together, red, yellow, and green. If I add them all up, I get to 180 degrees, since that makes a straight line from north to south. So I'm going to start with the equation, 180 degrees. Maybe let's slide that over to the left a little. Got more space to work. 180 degrees is equal to the sum of the three angles in color. 72 degrees, or 72 degrees, plus theta, plus beta. Red plus yellow plus green. So if I knew what theta was, if I knew what the yellow angle was, I could solve for the green angle. So that's the path I'm going to take. Come back to this triangle I just drew in. I know that those two sides are connected by the right angle. The two sides I know are right there. I don't know the hypotenuse. Also don't need the hypotenuse, so won't bother solving for it here. So my opposite side is 6.5 kilometers. My adjacent side is 3.5 kilometers. So I should set up a tangent equation. Since that's the trig function that relates opposite and adjacent together. 6.5 over 3.5. And then use a tangent inverse function to find my angle. This is tan inverse of 6.5 over 3.5. which, if you take that to a calculator and you're in degree mode, you should get 61.7. Once I've got that, come back to the original equation I had and solve it for beta. So 180 minus 72 minus 61.7. 61.7. And again, I think you could do all that in a calculator. I got 46.3. And that's in degrees. So the last step is to just put that thing into a bearing format. Looking back at my diagram, if I go from my start line to my finish line, I'm headed southwest. So my angle should, or my bearing should be southwest, or 46.3 degrees west of south. Right, the correct format is to just put the bearing angle in the middle of our cardinal directions. We're going southwest, we just put 46.3 in the middle of southwest. All right, the next couple of pages aren't going to be covered this semester. Again, this is for spring 2024. All of this is off of worksheet 8. So if you've looked at any of that material, I put in the answers here, but I won't be covering them today. And also, they're not going to be on the exam. That's why I'm just going to be skipping over them. So on to the next one that is on the exam, which is this guy right here. So we've got a thing. Finding all solutions for theta, given that cosine of theta is equal to -5/7. So when it says find all solutions for theta, that means we're going to be leaving our answer as a general equation of some kind. So we'll have plus 2k pi in our answer, because we're looking for all solutions. We'll start by finding all solutions that are just inside of one circle. But then we'll also say anything coterminal to what we initially find will also solve the equation. So just for right now, I'm going to come down to my answer box and write plus 2k pi in right away, just so I don't forget it later. But now, let's go through the step that we do every time we have one of these, which is just solving for a single circle. So between 0 and 2 pi, what answers can I come up with? So I want to start by noticing that cosine inverse is less than 0. So I'm ultimately going to be looking for solutions in quadrant 2 and quadrant 3. My solution should show up there. But before I do that, I'm going to need a reference angle. So to get that reference angle, I want to use a cosine inverse function. And here I'm specifically going to be doing the cosine inverse of +5/7. Since the reference angle always should come out in the first quadrant, so I should always be taking an inverse function of a positive value. So the cosine inverse of 5/7. If we switch our calculator back to radian mode, 0.7752. It's more space above. So now that I know my reference angle, I'll come back to those two quadrants I know I need to be in. In quadrant 2, I'm looking at pi minus the reference angle to get my answer. And in quadrant 3, I'm looking at pi plus my reference angle. to get that answer. So those are the two equations I'll use, and then go to a calculator to get the rest. This looks like pi minus 0.7752, which comes out to 2.3664. If I do that same thing, but do pi plus 0.7752, I got 3.9186. Again, all that you'll just go to a calculator to get. Wouldn't expect anyone to do that by hand. So our answers are those two values, 2.3664 and 3.9186. Both plus 2k pi. Because I know that anything coterminal to either of these two angles will also solve the original equation. Notably here, the reference angle itself does not solve the equation. I just need it to find my other two solutions. Then we go again. So doing this one more time, 5 sine theta minus sine theta tangent theta equals 0. And again, finding all of our solutions, everything that we can get. So the first thing I'll do is notice that there is a sine of theta in each of my two terms, meaning that could be factored out. So I'll have sine of theta times 5 minus tangent theta is equal to 0, which means I get a pair of equations from that. I get either sine of theta equals 0 or 5 minus tangent theta is equal to 0. Either one works. From the left side, I get two solutions, 0 and pi. So I'm going to add those two to my answer box, 0 and pi. From the other side, I'll get tangent theta is equal to 5. And I'll need a reference triangle to solve that bit. First part, I only needed the unit circle, so I just used the unit circle. For the second equation, I'll need that reference angle. So if tangent of theta is equal to 5, that means that our reference angle is going to be the tangent inverse of 5. And when I plugged that into a calculator, I got 1.3734. And then because tangent, back down here, tangent of theta is equal to a positive number, the other two solutions I should be looking for are in quadrant 1 and quadrant 3. Since those are the two quadrants where tangent is positive. So in quadrant 1, theta and the reference angle are one and the same. So that's just 1.3734. And in the third quadrant, I'm looking at pi plus the reference angle. And in a calculator, I got 4.5150. 4.5150. So I'll also add both of those two answers to the box. 1.3734 and 4.5150. And then don't forget that we were looking for all solutions for theta. So while all of those are the solutions between 0 and 2 pi, anything coterminal to one of these angles also solves the equation. So 4 separate equations, all of which solve the initiative problem. Let's see what kind of chats we have. Is this also in radians? Yes, it is. Hey, come back. And is there a way to determine tangent inverse of root 3? It's pi over 3, or is it just something we have to memorize? Yeah, it should be something that you just memorize, is the way I'd recommend that. Answer line. All right, and the last page, we might almost get this thing done before the end. Almost. This time, we'll just find all solutions in radian measure between 0 and 2 pi. So we don't need all coterminal angles this time. We just need everything within one circle. And this one's got cotangent squared plus 3 cosecant of theta is equal to 3. We've got too many different trig functions all happening at once right now. So I'm going to use a Pythagorean identity to change that cotangent squared. I know that cotangent squared is equal to cosecant squared minus 1 plus 3 cosecant theta minus 3 equals 0. I know ultimately I want to get this thing equal to 0. So I'll move that 3 over to the left side. And then start solving this thing out. This looks like cosecant squared plus 3 cosecant theta minus 4 equals 0. That is a factorable quadratic equation. Should factor to cosecant of theta minus 1 times cosecant theta plus 4. It's equal to 0. So that gives me two options. Either cosecant theta is equal to 1, or cosecant theta is equal to 4. And solve that for theta. The first one, I can just use the unit circle. If cosecant of theta is equal to 1, it means theta is equal to pi over 2. There's only one solution around the first circle, around 0 to 2 pi. So pi over 2 goes in the box. On the other side, if cosecant theta is equal to, that was equal to negative 4. Cosecant of theta is equal to negative 4. That means that sine of theta is equal to negative 1 over 4. And we'll get solutions based on a reference angle. Negative 1 over 4 isn't a value we know from the unit circle, so reference angle is what we'll need. This thing is less than 0. All right, sine of theta is equal to a negative number. So I'm going to be looking in the bottom two quadrants, which are 3 and 4. Where I'll need pi plus the reference angle. And in quadrant 4, I'll need 2 pi minus the reference angle. So I should just go and calculate what that thing is. Just make that a little more clear. So that reference angle, theta ref, it is the sine inverse of positive 1/4. And I got 0.2527. Once I've got that reference angle, I'll use my calculator to go get the other two actual solution angles. Pi plus that number, 3.3943. And 2 pi minus that number was 6.0305. So those two answers also go in the box. 3.3943 and 6.0305. All right, this one I didn't need all solutions, so I just stick with ones that are between 0 and 2 pi. Go to chat real quick. Actually, hang on one sec. All right, so questions from Zoom. For question 16, could we use a quadratic formula instead of factoring? Yes, absolutely you could. And why is it -4? So when I factored this thing, I got cosecant -1 and cosecant +4. This is what I got from factoring using or the quadratic formula. Then if it's cosecant -1 equals 0, it means cosecant has to be +1. If it's cosecant +4 equals 0, that means cosecant has to be -4. I'm just solving those two equations for 0. All right, and with the last problem that I'll cover today, finding the exact value for theta and radian measured between 0 and 2 pi for secant of 5 theta equals square root 2. This will be the same thing as cosine of 5 theta equals 1 over square root 2, which in turn is square root 2 over 2. So I'm going to look for angles within the unit circle where cosine is equal to root 2 over 2, and then come back and deal with the 5. So on the one hand, that input angle into cosine could happen at pi over 4, or it could happen at 7 pi over 4. Right, those are the two solutions between 0 and 2 pi. Pi over 4 and 7 pi over 4. Then I'm going to add 2k pi to each, and I'm going to do it in a different color on both sides. Because anything coterminal to either pi over 4 or 7 pi over 4 would also solve the equation. But now I've got to come back and deal with the fact that I had 5 theta instead of just theta. So let's put an or right there. So I should divide both sides by 5. This will be pi over 20 plus 2k pi over 5. Or if I get that into a common denominator, because I think that'll be helpful, we're looking at pi plus 8k pi over 20. Our common denominator between those two fractions is definitely 20, which means I need to multiply a 4 over 4 into the fraction on the right. On the other side, pretty similar looking steps. Divide both sides by 5. Gives me 7 pi over 20 plus 2k pi over 5. Or that's 7 pi plus another 8k pi over 20. All right, so those are my two solution equations. I just need to generate the first 5 solutions to each one. So starting from pi over 20, and then counting by 8s. So this will look like 1 pi plus 8 pi is going to be 9 pi over 20. Count by 8 again to get 17. Plus 8 again is 25. Plus 8 again is 33. If I'm counting by 8s, those are the coefficients I'll get in each of my numerators. So just fill in the rest. 9 pi over 20, 17 pi over 20, 25 pi over 20, and 33 pi over 20. Those are the first 5 solutions from the green equation. From the blue equation, I should start at 7 pi over 20. And again, count by 8s. So starting from 7 and counting by 8, I get 15. Plus 8 again is 23. Plus 8 again is 31. Plus 8 again is 39. And then each of those are pi over 20. 15 pi over 20. 23 pi over 20. 20. 31 pi over 20. And finally, 39 pi over 20. And those would be my 10 solutions that are between 0 and 2 pi. I missed on a clap. That's embarrassing. All right. And that actually takes us to the end of the review. So not too far over time. Any questions before I wrap this thing up? All right, cool. Well, good luck on that exam tomorrow, or if you're watching this Thursday morning, good luck on the exam that's in like not very long, maybe a couple of minutes. And yeah, that's all I got. Okay, bye.